Hi, my name is Matthew, and in this video we're going to talk about partial fractions. And in order to successfully make your way through partial fractions, you definitely need to have a good handle on systems of equations, both in 2 variables and in 3 variables. So if you still need to master that topic, go back and check out my previous videos. Otherwise, let's take a look at partial fractions. What you're seeing here at the outset of these notes is an example of a subtraction problem. And you've done problems like this in your recent studies. And the challenge, of course, in doing that particular subtraction problem is you need to achieve a common denominator. And so if we went through the motions and we created a common denominator, it would be x minus 4 times x plus 2, and you would have the numerator of the first fraction would have become this, and the numerator of the second fraction would have become this, and then you would distribute this multiplication by -2 in order to arrive at this numerator, and then you would combine like terms in order to finally get this numerator over your common denominator of x minus 4 times x plus 2. The real challenge, or certainly a real challenge, there are a lot of challenges in the world and in life, but in this particular case, a real challenge would be to try to work this problem backwards. What if I gave you this as the question, and this was to be the final answer? And that's what partial fractions is all about, is sort of reverse engineering the question for this type of a problem. Or, as we very often do in mathematics, is after we learn how to do a process in one direction, we then reverse the process. So, we'll just keep scrolling our way through here until we get to... So, what you're seeing in these 4 bullets, or in this enumerated list, is 4 different cases that we're going to be looking at. Your denominator could be a product of distinct linear factors, some of which are repeated. You could have a prime quadratic factor, and a prime quadratic factor is one that looks like ax squared plus bx plus c, where it cannot be factored into maybe the product of binomials. And then the 4th one is where you have a repeated prime quadratic factor. Now, none of that means a lot to you maybe at the moment. The word quadratic sounds familiar, linear sounds familiar, and linear should sound familiar from y equals mx plus b, right? That's slope-intercept form. And the mx plus b part is what we're seeing right here, except it's being written as ax plus b. And then down here, it's in the denominator under something, capital A, whatever that is. We're going to get to it. So this denominator is called a linear, the denominator of this fraction is linear, we'll call it. And it's called linear because if you put a y equals in front of it and you graphed it, it would look like a line. Line, linear, there you go. Now, it's possible that you could have a whole bunch of linear factors in parentheses being multiplied with each other in the denominator of a fraction. And your numerator would be some considerably complicated looking mess. And if you were to sort of decompose that and turn it into the sum, addition, 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 if you turned it into the sum of a bunch of fractions that had each of those linear factors from the first denominator, this denominator, this is pretty much the format that it would take on, right? So this thing that this arrow is pointing at currently, or let's actually do this. This would be the question, and all of this stuff would be the answer. All right, so as usual, that's all a little vague. I haven't even seen any numbers yet. So here we have the opportunity to look at a problem that has some numbers in it. And the instructions here say to write the partial fraction decomposition of the rational expression. So partial fraction decomposition is what we're going to be performing. And you'll find out momentarily why it is that it's important to have a really good handle on systems of equations in order to make your way through one of these problems. Now, the general format when we decompose this thing, I'm going to put an equal sign here, and I'm going to write this as capital A over x minus 2 plus capital B over x plus 1. And I want to tell you why I wrote that. What we see up here is a linear factor times a linear factor. And here, you're seeing that same linear factor and that second linear factor, except it's been broken up into the sum of two fractions. And what are those numerators? I see a sub 1 and a sub 2. Now in the problem that I'm doing with you, I wrote that as capital A and capital B instead of a sub 1 and a sub 2, which is fine. We can use A and B. How did I know to put an A and a B in my numerators? So right, I have an A and a B. Notice that this term right here has a multiple of x in it, right? It says a sub 1 times x. And this second term, b sub 1, does not have an x associated with it. So this term, the a sub 1 times x, is considered a first degree term. That term is degree 1 because the x variable is being raised to the first power. This term over here is degree 0 because it does not have an x variable associated with it at all. It's the constant term. So again, degree 1 and degree 0. The largest of those two numbers that I just wrote down is the number 1, which means that the entire denominator is degree 1. The numerator up here is the degree of the denominator minus 1. So this denominator is degree 1, which means that my numerator needs to be degree 0, which means that my numerator needs to be a constant and not have a variable associated with it. Very much like this decomposition here. Notice that there's a 3 in the numerator and in the first numerator and a -2 in the second numerator. And look at these denominators. This one's linear. It has an x to the first power. This one's also linear. X to the first power is the biggest power. Okay? So you will need to maintain that relationship as you do partial fraction decomposition. Will we run into problems that have an x squared down here? That's a second degree denominator. Absolutely, we're going to in this video. Does that mean if this denominator were degree 2 that my numerator would have to be degree 1? Yes. What's that going to look like? We're going to get there. Don't rush it. I promise we will get there. Okay, now I took each of my factors from my original denominator and I put them into... Each factor is now appearing alone in its own denominator. Great. And those are linear factors in the denominator, which means that my numerators are going to be constant values. There they are, a and b. So now that I know the format of what the process sort of starts out looking like, what do I do next? The next thing we're going to do is what I love to do whenever possible when I'm working with fractions is I'm going to get rid of all the fractions. I'm going to take this entire equation and I'm going to multiply it by the lowest common denominator, or least common denominator, which means I'm going to take the entire equation and I'm going to multiply it by x minus 2 times x plus 1 over 1. What I do to one side of an equation, I must do to the other, so I am multiplying both sides by the same stuff. I'm going to take that stuff, the x minus 2 and the x plus 1, which is the LCD, and I'm going to multiply it over here to my first numerator, and I'm going to multiply it into this one, and I'm going to multiply it into this one. All right? I'm going to write it out. So it's going to take a little doing. Let's see. We'll go as quickly as possible. So the first numerator already has... I already screwed it up. Take 2. Take 3. Our first numerator has a 5x minus 1 in it, and we're also multiplying in an x minus 2 and an x plus 1, and all of that is being divided by its original denominator of x minus 2 times x plus 1 equals. In my next fraction, there was an a there, but we're multiplying in an x minus 2 and an x plus 1. And that's all being divided by the denominator that was already there, which was the x minus 2. And then in our last fraction, its numerator already had a b. We're multiplying in the x minus 2 and the x plus 1, all divided by its original denominator of x plus 1. Why did I multiply in all of that stuff? So that this can happen. The x minus 2's are canceling, the x plus 1's are canceling, these x minus 2's are canceling, these x plus 1's are canceling, and I have no more denominators, which means I've got no more fractions. I love that, because I don't really love fractions. You need to know how to work with them, but you also need to know how to make them go away. We've just made them go away. Let's write down what we have left. On the left-hand side of our equation, we have a 5x minus 1 equals, on the right-hand side, there's a capital A, times the quantity, x plus 1, plus capital B, times the quantity, x minus 2. Very nice. So we multiplied by the LCD over 1, and then we reduced. And now I'm going to distribute. The left-hand side's not going to change. But the right-hand side is where the distribution's happening. You can continue rewriting the left-hand side. I usually get lazy and don't write it over and over again, but you can certainly do that. The next thing I'm going to do is regroup these a little bit. I'm going to put the terms that have the x variables in them, I'm going to write those first on the right-hand side, and then I'm going to write these constant value terms after that. Let me show you. Left-hand side stays the same. Regroup is a little bit of a sort of a casual term. That's not a technical term. I suppose commuting would be the technical term for what I just did, using the commutative property of addition. I just massacred that capital A right there, but it made me feel better about myself. The next thing I'm going to do is a little bit of factoring. And this is going to be unusual. Check this out. These first two terms contain a multiple or a factor of x. I'm going to factor the x out, but instead of writing it to the left of my parentheses, I'm going to write it to the right of my parentheses. Because imagine that this said 3 and this said 5. If it was 3x plus 5x and you combined like terms, what would you get? You should have said 8x. How did you get that? You took the 3 and the 5 and you added them together. So the a and the b added together tell me how many x's I have. So I'm going to add the a and the b together, and that tells me how many x's I have. We do still have plus the a, which is a constant value, minus the 2b, which is a constant value. Now, this is an equation, which means the amount of x stuff that we have on the left-hand side must equal the amount of x stuff that we have on the right-hand side. and the amount of constant stuff that we have on the left-hand side must equal the amount of constant stuff that we have on the right-hand side. That's sort of technical language that I just used. X is technical, constant's technical, so let's set those two different amounts equal to each other. I'm going to switch colors, and I'm going to say that 5x on the left-hand side, I have 5 x's on the left-hand side, so that better be equal to the number of x's that I have on the right-hand side. I'm setting their coefficients equal to each other. You could even say I am equating the coefficients. How much constant, oh wait, on the left-hand side, instead of writing 5x, we just want a 5. We're only setting the coefficients equal to each other. So 5 is how much x I have on the left, a plus b is how much x I have on the right. My constant amount on the left is -1. My constant amount on the right is a minus 2b. You should describe the creation of this however you want. Right here is where the description should go for how we went from that line down to this line. Equating the coefficients, equaling x stuff and constant stuff between the two sides of the equation. Whatever language, however you want to phrase it, write it so that it's going to make sense for you. Okay, I don't think there's a standard language on that one in terms of how it should best be phrased. What you should realize, however, is that we just created a little system of two equations with two variables. Instead of x's and y's, we've got a and b. And the next thing we're going to do is solve this system of equations. And I'm going to solve it using subtraction. It's a little unorthodox. The two types of solving systems of equations, the two methods that we used previously were substitution and addition. But I'm going to, instead of taking the time to multiply one of them by -1 so that I can add them together, I'm simply going to subtract. 5 minus -1, and if you want to put a minus sign in parentheses over there, you can. 5 minus -1 is equal to 6. A minus a is equal to 0 a's. Positive b minus -2b, so be careful with the double negative there also, leaves us with 3b. And then we can divide both sides by 3, and we get 2 equals b. Now we can take that and substitute it back into either one of our original equations. I'm going to substitute it into equation 1. Let's see, into 1, so that I get 5 is equal to a plus 2. And if you want that 2 in parentheses where you did your substitution, that's fine. And then I'm going to subtract, not 3. My pen is like skipping on the screen, and I don't know why. So we're subtracting 2 from both sides, so that we get 3 is equal to a. So those are our a and b values, and let's double check where those came from. They came from the very beginning of this conversation. They came from up here. There's my a and there's my b. I'm going to put them back there. I'm going to rewrite these two fractions as my final answer. And if you want, you could rewrite this entire equation. The original fraction equals our new a and b values over those denominators, x minus 2 and x plus 1. And if you'd like, as I said, you can rewrite this first fraction, 5x minus 1. But this is really your final answer. And that is partial fraction decomposition. There's not any heavy math that happens in here. It's a little bit of a lengthy process, but group it into steps, or sort of group these steps. The first thing that we did was we had to make sure that we had the correct format up here, especially right here with the A and the B in the numerator. The next part of the process was getting rid of those denominators. So that involved multiplying by the LCD over 1. And once we did that, the next real goal was getting our equations to this point where it allowed us to set the left-hand stuff equal to the right-hand stuff, or the amount of left-hand stuff to the amount of the right-hand stuff, which allowed us to build our little system of equations. And from there, you should really already know what you're doing in terms of solving that system of equations. So this part of the process, or at least this part of the process where you're solving the system, that's not new. This is the new stuff that you're learning up here. All right? And all it involved was a little bit of manipulation, right? None of this stuff even involved any actual math. Right? You never multiplied a single number together, you never FOILed anything, distributed anything, combined any like terms or anything. So that's a very process-oriented thing, right? Step, phase of this decomposition that you need to commit to memory. After that, putting this stuff onto a flashcard, distributing, regrouping, factoring so that you can equate the left and right hand stuff to each other. So technical is my language. All right, so practice some of those. The process should be pretty much the same every time when you have a couple of linear factors in the denominator like that. Steps in partial fraction decomposition. So here is somebody else's articulation of how to go through that process. Why it is that this box did not appear before we just went through that process, I don't know. However, I'm not going to read this. I'm not going to read it to myself. I'm not going to read it aloud to you. You should read it and see if you like bits and pieces of the way that it's phrased here compared to the notes that you've already taken, and maybe modify your notes if you like some of this language better. Now, here we're looking at the possibility of having some repeated linear factors in the denominator. So not only are we having an a plus b in the denominator, but that a plus b is now being raised to the nth power. And to the right of that, you're seeing 1, 2, 3, etc., all the way up to the nth instance of that linear factor. So if it were ax plus b to the third, you would have ax plus b to the first, ax plus b to the second, and ax plus b to the third. Okay, and you wouldn't have any of the rest of this stuff. So let's see how that plays out here in example 9. We're only going to write the form of the partial fraction decomposition. Okay, we're not going to go all the way through and solve for a and b. So here, I know that I'm going to have a denominator for my x plus 1 plus a denominator for my x minus 2 to the first power and a denominator for my x minus 2 to the second power. So the x plus 1's going here, x minus 2 to the first power is going there, and you could do this, put it to the first power. Nobody writes it that way, but if that helps you to see the pattern, that's fine. And then there's an x minus 2 to the second power. And if you want to, scribble out this 2 and make it a 3. And that way you have to add another one onto here. Okay, you keep making that exponent bigger, you have to keep adding fractions on following this pattern. Now, every one of these is still considered a linear factor, all of them. Even though this is being raised to the third power, what's being raised to the third power? A linear factor. So linear. That's first degree, x to the first power, which means all of our numerators are going to be 0 degree, which means they're all going to be constant values, which means I'm going to write in numerators of a and b and c and d. All of those are going to turn out to be numbers, just like in the previous problem that we worked where a and b turned out to be numbers. So this would be your final answer to this question. And if you're one of my students, you're going to have a question or 2 or 3 where you have to write out the form of the partial fraction decomposition. This is what your final answer would be. I would not include this first power in there. Just put a regular old x minus 2 under that b value. Excuse me. So that's 2 out of 4 of the scenarios. The next one is where you have a prime, non-repeated quadratic factor in the denominator. And there's that quadratic factor, ax squared plus bx plus c. And it cannot be factored. Now, can you have a quadratic factor that does not have this bx term in it? Absolutely. A quadratic factor must have the squared term. It's got to have that squared term, but it doesn't have to have the bx term. It doesn't have to have the constant term either. You could just have an x squared all by itself, and that would be a quadratic factor. In example 10, one of the factors in our denominator is a quadratic. It's a second degree polynomial. That's another way we can phrase it, because it has that x to the second power. And let's take a look at what this decomposition looks like. Well, actually, go back up to the top of your screen with me. So this fraction has that quadratic factor, which is a second degree. Okay, denominator is degree 2, which means numerator has to be degree 1. Remember that when we do these decompositions, the numerator will end up being 1 degree less than the denominator. So in that numerator, we only have an x to the first power, whereas in the denominator, we have an x to the second power. All right, I've made a mess out of that. Let's start on example 10. I'm going to have 2 fractions resulting from doing my decomposition. My first factor is an x, or my first denominator, which contains my first factor, is an x minus 4. The second one contains the x squared plus 5. Now the x minus 4 is linear, degree 1, which means that the numerator is going to be a constant, degree 0. My second denominator, x squared plus 5, is degree 2, which means that the numerator needs to be degree 1. It's going to look like a linear factor, and I'm going to write that as bx plus c. Right? Because it has to have that x to the first power in it, and the plus c gives us the opportunity for there to be a number after it, just like y equals mx plus b. This is bx plus c. That is a linear first degree factor in the numerator. And then we could go through and multiply this entire equation by x minus 4 times x squared plus 5 in order to sort of get the ball rolling. And what I'm going to do is I'm going to take you through that process right up until we create the system of 3 equations. And since I've already taught you how to process or solve a system of 3 equations in 3 variables, I'm not going to show you how to do that again. But since this first part of the process is new to most of us, let's go through it together. So again, I'm going to use that technique of taking my entire equation and multiplying it by the LCD over 1. In this case, I'm multiplying by x minus 4 times x squared plus 5 over 1. And I like to put it over 1 to remind myself I'm only multiplying it into the numerator. Now, I'm not going to write out as much this time as I did last time. As I multiply this into here, and you could write both of those terms or factors into that numerator, and multiply this numerator by both of those factors, and multiply this numerator by both of those factors. I'm going to do that multiplication in my head, dropping those into each numerator, and I'm going to reduce all in my head. So when the x minus 4 and the x squared plus 5 join into my first numerator over here, when they come in over here, that's going to cause the x minus 4 and the x squared plus 5 to cancel out from that denominator, leaving me just with the numerator over there, 5x squared minus 9x plus 19. Now if you need to write out all that multiplication, pause this video, multiply the LCD into all three of your numerators, do the canceling like we did in the very first problem, and then start writing down what's left. I'm going to jump right to writing down what's left. Equals. These two things multiply into this first numerator. The x minus 4s are going to cancel, but the x squared plus 5 is still going to be there. So the a is there, the x minus 4 is canceled, but the x squared plus 5 remains. Plus, I multiply these two factors into this third numerator. The x squared plus 5 is going to cancel with this x squared plus 5, leaving me with the original bx plus c that was there, and the x minus 4 will still be there. So just getting to this point does require some organization, okay? So take it slow, be skipping lines if you're using lined paper. Give yourself some room for your eye to see each individual step as you're marching through this process. All right, if you refer back to the first decomposition that we did, the next step is to distribute. In this case, I'm going to be distributing here, and I'm going to be foiling over here. Left-hand side stays the same. Right-hand side becomes ax squared plus 5a plus, and then we're foiling now, bx squared minus 4bx plus cx minus 4c. And then I'm going to regroup. Let's write our squared terms first. That's ax squared plus bx squared. So I've got those. Now let's go for our x to the first power terms, our linear terms. That's a minus 4bx and a plus cx. So that's this one and this one. Good. And now our constant terms, that's a positive 5a and a negative 4c. All right, we got them all circled and circled. Nice. Now let's do our factoring. And we're going to factor twice this time. We've got some factoring that we can do here, and we have some factoring in our x terms. So the common factor in the first group is the x squared. How many x squareds do I have? I have a plus b of them. A plus b x squareds. And how many x's do I have? I have, now this is a little tricky here. I'm going to say I have plus, I don't know why my pen is being so jittery. It's like stuttering across the screen. There we go. A plus negative 4b plus c x's. You may have never written anything like that in your algebra career thus far, okay? So what's happening is I'm adding a negative here, which is like doing subtraction, which is what I was doing, subtracting 4bx. And I've also got, I'm adding this positive c, which is happening up here. There's that adding of the c. So all of this is, it's all legit. It all works out. If you wanted, you could take this x right here and bring it over here and write it as plus x times that stuff. And then if you distribute the multiplication by x to the negative 4b and to the positive c, you will get this stuff up here again. All right? Not that you didn't trust that I wasn't doing the math right, but I want you to see why it works the way it is that I'm laying it out. And remember, the reason I'm organizing things the way that I am is because of the next step that we're going to do. So let's try to get there sometime before the sun rises, shall we? Okay, so now here's where you're calling it whatever you want to call it. I'm going to actually write in the left-hand side again. Let's get that 5x squared minus 9x plus 19 into the mix again, because now we're going to equate the amount of stuff on the left-hand side to the amount of stuff that's on the right-hand side. So how many x squareds do I have on the left? I have, let's switch colors, I have 5x squareds. How many x squareds do I have on the right-hand side? I have a plus b of them. How many x's do I have on the left-hand side? Negative 9 of them. How many x's do I have on the right-hand side? I have negative 4b plus c of them. I'm equating the coefficients. Negative 9 is the coefficient on x on the left-hand side. Negative 4b plus c is the coefficient of x on the right-hand side. Let's equate our constants. I have positive 19 as a constant value on the left, and I have 5a minus 4c on the right-hand side. And we have, if we label these 1, 2, 3, we've created our system of equations. Not bad. Now, this system of equations is a little bit unusual because each one of the three equations is missing one of the terms. So you have to decide which of the variables you're going to eliminate. Typically, I choose, well, in a system of three equations where one of the variables is already missing, I would say pick a variable that's already missing and choose that one to eliminate again. In this case, in equation 1, c is missing, and in 2, a is missing, 3, b is missing. So you already have one instance of one of the variables missing, so that covers all three of them. I think you see what I'm trying to say there. A, b, and c are missing. So then you still have to choose. The next sort of guide that I use to help me choose which variable to eliminate is I eliminate one that has a coefficient of 1 because it's easily modified. For example, I could take this a right here and multiply it by negative 5 so that it becomes a negative 5a, so that when I add it to this positive 5a, they cancel out. Or I could take this equation 1 and multiply it by positive 4 so that when I add it together with equation 2, my b's would cancel out. Or take equation 2 and multiply it by positive 4, so that when I add it to this negative 4, those cancel out. So if you're looking for a specific recommendation, any one of the three that I just listed are perfectly good. If you just want me to tell you what to do, realize that I'm just sort of randomly picking one of those three options, I would say take equation number 1 and multiply it by 4 and then add it to equation 2. What's going to happen is you're going to let's just do it, shall we? I've already spent enough time talking about what you should do. Let's just go ahead and do it. It's nice because we're already going to have one of the equations done for us. Let me explain. I'm going to use equations 1 and 2 to eliminate the b term. Since I'm going to be eliminating the b term, normally you would do that twice in order to create equations 4 and 5, where equations 4 and 5 are both missing the b term. In this case, equation 3 is already missing the b term. So I'm going to say that equation 3 is also equation 4 missing b term. Now let's take equation number 1 and multiply it by 4. So I would skip a line if you're using lined paper. Multiplying by 4 makes this a 20. Changes the a into a 4a, changes the b into a positive 4b. And that is equation number 1. And what I did, if you just look up at the original equation number 1, I'm taking it and multiplying it by positive 4. And the result I would not draw that arrow, but if you'd like to have that arrow, you could do that. Multiplication by 4 turned it into that version of equation 1. Now below equation number 1, I'm going to write equation 2. So there's the negative 9 equals a little space, the negative 4b, and the positive c. That's the original equation 2. I would draw a line, and we're going to add these two equations together. 20 plus negative 9 makes 11. The 4a sticks with us, the b's cancel, the positive c is still there, and that is equation 5. So you've got equation 5 there. Equation 3 is equation 4. So I'm going to be combining equations 4 and 5, and remember, this is equation 5, equation 3 is equation 4, and I'm going to combine those. I'm going to add them together actually, but before I add them together, in order to cancel out my c terms, I'm going to take equation 5 and multiply it by positive 4. So let's multiply it by 4, skip a line, then we have 44 is equal to 16a plus 4c. That's still equation 5. Below it, I'm going to write equation 4, formerly known as equation 3, which is 19 equals 5a minus 4c. That's equation 4. I'm going to add these together now. And once I add these together, I'm going to have a real idea as to whether or not I'm on a good path and whether or not I've made any arithmetic mistakes. 44 plus 19 is 63 and equals 16 plus 5 is 21a. My c terms canceled out, and sure enough, both sides of this equation are very easily divided by 21. So let's divide both sides by 21, and that gives us 3 equals a. Now we're going to take that a value and we're going to plug it back into equation 1 in order to find our b value, and then we'll plug it into equation 3 in order to find our c value. Now I've run out of space here in these fill-in-the-blank notes, so it's going to get a little tight here. I apologize. Equation 1 sub into 1 and 3. All right, going into equation 1 gives us 5 equaling our new a value of 3 plus b, and I'm just going to draw a little line, or a little arrow rather. Subtracting 3 from both sides tells us that 2 is equal to b, and I'll circle that so it doesn't get lost. And then let's plug our a value into equation 3. That says 19 equals 5 times our a value of 3 minus 4c, and if we subtract 15 from both sides, we find that 4 is equal to negative 4c, and then if we divide both sides by negative 4, we find that negative 1 is equal to c. Let me circle that. Now it's been so long, and in fact, in the middle of this problem, I went and had a dinner break. I've got company in town, and there was a little knock at my door, maybe you heard it, and I was getting called for dinner, so I have no idea. I really can't remember what the original decomposition looks like. There it is. So there in red are our a, b, and c values. We've got a over x minus 4 and bx plus c over x squared plus 5. So I need an x minus 4 and I need an x squared plus 5. Those were my denominators. My a value, there it is a 3. And my second numerator said bx plus c. So that's 2x bx. And then you could write plus negative 1, but I think it's a little more customary to just write minus 1. And there, my friends, is the partial fraction decomposition. That was a good one. That involves a lot of steps, a lot of organization, a lot of labeling, but ultimately the strategy in this problem is identical to the strategy in the first shorter problem that we worked with, where we only had to solve a system of 2 equations. We did the initial format for the decomposition. Once we did that, we multiplied both sides by the LCD over 1. And then we went through the sort of cleanup process necessary to allow us to set our coefficients equal to each other. And when we did that, that's what gave us our system of equations. And then you already knew how to solve a system of 3 equations, but we went through the process in order to find our A, B, and C values, and then we plugged those. And I didn't really write a note about how we went from here down to this final answer. So if you want to write in a little note to yourself about how we went from those solutions into that final answer, you can put that note in your own words. And then I want to go into our very last subtopic. I know that we're 45 minutes in, and these full lectures can be a little long and a little time consuming and drone on a little bit, but I appreciate you hanging with me because I'm really trying to give you the full detailed picture of what's going on with these different processes. So the last subtopic is when we have a repeated quadratic factor, and here's the format for a repeated quadratic factor, and very similar to when we had a repeated linear factor. If it's being raised to the 3rd power down here, then you would have 1, 2, 3 instances of that denominator. Let's see what it looks like. Oh, this is nice. This is set up as a multiple choice question for us. I'm going to actually go ahead and write it out so that I can match it up with the correct multiple choice option. I see the x minus 1 in the denominator, and it's not being raised to any additional powers. So I'm just going to write it once, plus, and then my second denominator, oh, I see that I have an x plus 3 that's being squared in my denominator. And since it's being squared, I know that it's going to appear twice. It'll be the x plus 3 to the 1st power, and then when we see it again, the x plus 3 will be raised to the 2nd power. Plus, and now I've got an x squared plus 1 that's being raised to the 2nd power. And oh, I moved my screen over, and this stuff moved for some reason. I don't know. If I zoom out, does it move back? Of course not. Let's try that again. There's the x plus 3 to the 1st power plus the x plus 3 for the 2nd time squared. Okay, and now our 3rd factor in the denominator is the x squared plus 1. I see it's being raised to the 2nd power, so it's going to appear twice. The x squared plus 1 appearing the 1st time, and the x squared plus 1 appearing for the 2nd time where it's squared. So if you add up the exponents in this original denominator, there's an invisible exponent of 1 right here. 1 plus 2 makes 5. And how many fractions did we end up with in the decomposition? 5 fractions. So that's a good way to narrow down just in case you're in a multiple choice situation. But even as you start laying out the format for the partial fraction decomposition, you should know pretty quickly how many fractions you're going to have. Okay, let's fill in the numerators. My first denominator, x minus 1, that's a linear factor, which means it's going to have a constant value in the numerator, a. Second denominator, x plus 3, that's a linear factor, which means it's going to have a constant value as a numerator. Third fraction, denominator, is a linear factor, x plus 3, that's being squared. I don't care that it's being squared. The fact that it's an x plus 3 at its core, and that that's a linear factor, that tells me that my numerator is again going to be a constant value. Now, my fourth denominator is a quadratic. It has an x squared in it. It is a 2nd degree polynomial, which means the numerator is going to be a 1st degree polynomial. We call that a linear factor, like mx plus b. This time it's going to be dx plus e. And finally, our last denominator is a quadratic at its core, which is second degree. So it gets a first degree or linear numerator, fx plus g. That is the form for our partial fraction decomposition, and let's see which multiple choice option it matches up with. It is the first one, which is written far more clearly than my handwriting, so double check, make sure you wrote all that down correctly. And that, ladies and gentlemen, is the end, thankfully, of our conversation about partial fraction decomposition. It's all 4 of the different scenarios that you're most likely going to run into, and we got to do a little review of solving systems of equations, both with 2 equations in 2 variables and 3 equations with 3 variables. Oh, what a joy it was. Thanks so much for hanging with me on this one. I'll see you next time.